Okay, so now we have symmetry. So there are three types of symmetry. We have y-axis symmetry, we have x-axis symmetry, and then we have symmetric to the origin. So I briefly already spoke about the y-axis symmetry and the origin symmetry. So y-axis also means that we have an even function. Origin means that we have an odd function. X-axis symmetry is kind of, I don't know, not wonky, but it's like a loophole because x-axis symmetry, like here's an example of something that has x-axis symmetry. Well, its whole deal is that it's not really a function, right? We fail that vertical line test. So it does have symmetry, right? Because symmetry is just basically whatever line we could fold across and still have the graph reflect itself. So it is symmetry, but our class mainly focuses on functions. So we're not going to talk about x-axis symmetry a whole lot. But essentially, if you plug in a negative y and get positive y in return, then your x-axis symmetry. Oh, and then really broad strokes, if y squared is in the equation, you know automatically you have x-axis symmetry. Again, that's really broad strokes there. So popping back over to the y-axis symmetry, it's even. So we already talked about that if x, y is on the graph, then negative x, y is on that graph, okay? So how we test algebraically is you sub in negative x, and in return, you get just y. So for the origin, very similar, except if you have xy on its graph, then the graph will have negative x, negative y, right? Because of that, oops, sorry, you can't see, let me zoom out. Because of that like double flip that I talked about, that twofold symmetry, right? Because you gotta fold down and fold over, right? So that means that your x's have to negate and then your y's have to negate. So how to algebraically solve it is you would sub in negative x again, but here in return, you get negative y, okay? So to show you whether the graph of x equaling y squared minus 1 is symmetric with the y-axis, x-axis, or the origin, well, I look at it and I was like, oh, there's that pesky y squared. I know that's x-axis symmetry, okay? Also, because this then is a graph that looks something like that. Oh gosh, not to scale, not to scale. What are my graphs ever really though? What an ugly parabola, okay? But again, if I go through it and I say, okay, if I pop in negative x, and then I see what the output is, well, that's negative x equaling y squared, which is none of these options above. So it's not even, it's not odd, right? Because I didn't change the y and it wasn't exactly the same thing that I got in return. Because if you think about it, if I divide by -1, divide by -1, then x equals negative y squared minus 1, which is negative y squared plus 1, which is not what we started with, and it's not the exact opposite of what we ended with. No, not the exact opposite of what we started with. So 3 is x-axis. Again, mainly what your quickest way to determine is that it's got that y squared in there. So now, example 4, determine whether the graph of y equaling x cubed is symmetric to the y-axis, x-axis, or the origin. Again, I can nix the x-axis because it doesn't have a y squared in there. So bloop. Now the origin, how to determine if we're y-axis or x-axis symmetric? You can always graph it, okay? You can always graph it. The graph looks like this, which I showed you a page ago. Again, pretend like that is pretty, okay? So does this have that twofold symmetry that origin requires? So think of it as like putting down your push pin and then fold and fold. And again, if I could draw, the two branches would lie on top of each other. So origin is also what's known as an odd function. Origin, odd, OO, one way to remember. Y-axis symmetry is even, okay? Y-axis symmetry is even. But again, you can just graph and see that as well. So example 5, we go even further. I know, get excited. Whoop, whoop. We go even further into that even and odd functions. So determine whether each graph is even, odd, or neither. Well, remember that even is y-axis symmetric, odd is origin symmetric, and neither is it's just crazy. So I want you to pause the video and just see for yourself whether you can get correctly what A, B, and C, what type of function they are, and then press play when you're ready. Okay, so A, you can do this visually. Would y'all agree that it follows that twofold? So this has origin symmetry. So that means that it is also odd. Remember, O, origin. B is even, because even also means AKA y-axis symmetric. And then C, it's just one little hump, bloop, so it is actually a neither. Yeah, hopefully. How'd that go? Not too bad. If y'all have questions, just type them down or write them down and send them to me or ask them in class next time I see you. So example 6, determine whether each of the following is even, odd, or neither. Well, remember that if any of these have a y-squared, that is the, oh, we're not doing x-axis, so never mind. So just y-axis, origin, or neither. Remember, this is also even is y-axis, origin is odd, neither is, of course, neither. But one super duper cool thing is that if I'm even or odd, all of my powers will be even. So if you look at B, I have a x to the 4th and minus 2x squared. Since both of those powers are even, I know that it's going to be even. If I look at A, remember that, well, anything that doesn't have a power has the invisible power of 1. So same argument for B. Because 3 is odd and 1 is odd, I know that it is odd. So it is also symmetric to the origin, and I forgot B, if it's even, it's also symmetric to the y-axis. Okay, so here, if you have just all odd powers, it's odd. If you have all even powers, it's even. Then, if you have a commingling, which is what the case is here, and recall that this is technically 1 times x to the 0, because anything to the 0 power is 1. So here, if I have an even power, remember this is an invisible 1, an odd power and an even power, what do you think takes over? It's actually neither. If you have a commingling, it's neither. Algebraically, how to determine is you pop in your negative x and see what gets spit out. If it's the exact opposite, meaning all of your signs change, then it's odd. If you put in your negative x and you get the exact same thing in return, then it is even. So here's the setup for both A and B. I want you to pause the video and just see what you get. See if algebraically we do reinforce odd and even respectively. And then when you're done, come back, press play. Okay, so 3 negatives means overall negative. So I have a negative x cubed. Negative times a negative is a positive. So I have plus 6x. but this is also the negative of x cubed minus 6x. So we do have that if I pop in negative x, I get negative y, or notice that all the signs changed. Here, right, 4 negatives make a positive, so that's just x to the 4th. 2 negatives make a positive, so this just stays 2x squared. So again, if I pop in negative x, but I get the original in return, then I know we're neither. And I want y'all to try C. So pause and then play when you're finished. So C, if we pop in that negative x, we'll see that there's a commingling of the sign changes. Some do, some don't. And that's that's not what we want. C plus 1. So that would be x squared minus 2x plus 1. So notice we don't have the exact same thing we started with. Not every single sign changed. So therefore it's not even, because that would give us the exact same in return. It's not odd. That means every single term had a sign change, or the exact opposite, meaning opposite of positive to negative or negative to positive. So again, also reinforces that we are neither.